So as you can see, doing calculations in chemistry class, you have to put a little bit of thought into how you're going to report your answer. And so a lot of times people say, oh, I got an accurate answer, or I got a precise answer. A lot of people think that the terms accuracy and precision are interchangeable, but they're not. There's a very distinct difference between them. Well, what is the difference? What's the difference? Well, let's talk about it. A measurement is said to be precise if it yields very similar results when repeated in the same manner. For instance, let's say we measured using a graduated cylinder a volume of water, or maybe I gave it to a bunch of different students and had them read the volume. One person said it was 32.5 milliliters, or maybe they got 32.5 milliliters. I gave a sample to another student and they measured with the same device. They got 32.4. Another person got 32.5 milliliters. Another one got 32.6 milliliters, etc. Those are what we would say to be precise answers. They are all very close together. They're only different in the last decimal place. Now, a measurement is considered accurate if it yields a result that's very close to the true or accepted value. So we often use an analogy with throwing darts or archery to give you a visual difference between the words accuracy and precision. So if you're throwing darts, you can be close to the bullseye or you can be far from the bullseye. So in one case you're accurate, and in one case you're not accurate. So let's say in this first case you have 3 darts thrown and they're all near the bullseye and they're all very close together. So this we would say is they're precise and accurate because it's repeatable. So whoever's throwing these darts is repeatable. They have a result that's very repeatable. They're all close together. This one here, these arrows are close together, so that would be this case here. This second case, these arrows are close to one another, or the darts, we'll say they're throwing darts. These are close together, but they're not on the target, so they are precise but not accurate. That's the difference. This is precise and accurate. This is precise but not accurate. Just like our series of measurements, we're all close together, so we say the measurement is precise. And the third case would be this one here, where your 3 darts that you throw are not close to the bullseye, so they are not accurate, and they're not really close together, so it's neither precise nor accurate in that case. That is the difference between the two. Another, if you look at a lot of research papers or journal articles, you'll see a lot of data. Well, you're going to acquire a lot of data in lab as well, so I want you to appreciate the difference between accuracy and precision. So this table here shows the volume of cough medicine delivered by a 10-ounce or 296 milliliter dispenser. So let's say we were testing the accuracy and precision of this dispenser. They probably actually have to do this in companies that make, syringes or, measuring devices. They have to test them to make sure that they, number one, give you the accurate results, but also give you results that are repeatable. They're consistently giving people the same answer no matter who's using it. So if you just look at data like this, dispenser number 1 that they delivered the cough medicine from had a series of measurements. They all kind of look close together, 283.3, 284. They're all not too bad, too far apart. Compare that to this one here. This is 298.83, 294.2, 296, etc. We want to get, it says it's a 296 milliliter dispenser. So think about is that accurate and precise, or just accurate, not precise? This one here is giving us values that are close to 296, and they're all pretty close together. So to summarize, this dispenser here, dispenser number 1, It's precise, but it's not accurate. See, they're all kind of close together, but it's not close to 296, which is the acceptable answer. So it's not accurate, but it's precise. Dispenser number 2 would be accurate. It's giving you a value that's closer to 296 than these are, so it's more accurate, but it's less precise than this one, because it ranges from 298 down to 293. That's almost 5 milliliter difference. This one only had a milliliter difference between all the measurements of, it looks like, 2 or less. This dispenser number 3 would be considered the best one. It's both precise and accurate. So let's look and see why that is. Because it's giving you 296 pretty darn close every time. It's only off by about 1/10 of a milliliter. And they're all the readings, the 5 different trials are all very close together. So you'll get a lot of practice with that sort of thing in labs when you do multiple trials and experiments. The reason why we do multiple trials or attempts at an experiment is for this very reason, to make sure the results are repeatable or reproducible and that you're getting close to the right answer. I believe the last section of the book, or I'm sorry, chapter 1, is probably one of the most important things you're going to learn in this class, and that's called unit conversion. Your book might call it dimensional analysis or the factor label method. I call it unit conversion. We're going to use it to carry out unit conversions for a given property, some measurement, and compute some answers. A quantity of interest may not be easy or even possible to measure directly, but instead must be calculated from other directly measured properties and appropriate math relationships. So it's very useful to do this unit conversion. The gist of it is pretty straightforward. You take a unit, let's just call it unit 1, and you multiply it by what's called a unit or a factor, or a unit conversion factor, or a factor label. Many names for these things. I just call it a fraction. It's unit 2, the new unit, over unit 1. And you treat units just like numbers in algebra. If the same unit is on opposite sides, this one's on the top, this one's on the bottom, you get the new unit left on the top. That's the gist of the process. So let's go through some examples of that. The key point to remember before we try that is that it's based on the premise that units of quantities must be subjected to the same mathematical operations as their associated numbers. So a conversion factor or unit conversion factor is just a ratio. I call it a fraction, but you can call it a ratio as well. It's a ratio of 2 equivalent quantities expressed with different measurement units. So for example, the lengths 2.54 centimeters and 1 inch are considered equivalent, so we just say they're equal. So you can write 2 conversion factors for that. I could write 2.54 centimeters over 1 inch, but that would be equal to 1 inch over 2.54 centimeters. I get 2 conversion factors. Every time I have a definition, I get 2. And there's some common conversion factors. There's no need to memorize these. The relationship between a meter and a yard's just a little bit less than a meter, so it takes a little bit more than 1 yard. This is one of the few exact relationships. 1 inch is exactly 2.54. Relationship between kilometers and miles, and so forth. So you're going to need to, I'll give you a chart like this on quizzes and exams. You don't need to memorize this sort of thing. We must use the form of the conversion factors that results in the original unit canceling out, leaving only the sought after unit. So let's try some simple examples, and then we'll work up to a few more complicated ones. Let's convert 34 inches to centimeters. Now you can try to do it in your head. You might think, oh, that's so easy, I can just do it in my calculator. But if you wanted to show somebody how to do it, you would write something like this: 34 inches like this. And now I want to convert it to centimeters, so my new unit, centimeters, would be on the top. and the inches would be on the bottom. Remember, the unit you're canceling has to be on opposite sides of this ratio or this fraction. But now you need to put in numbers to make this a true statement, or the number 1. So that's all unit conversion is. It's taking some unit, some measurement, multiplying it by the number 1. So I'm not really changing the size of the number, I'm just changing the unit. So that's why this method is so powerful. 2.54 centimeters over, I'm sorry, I already had the number or the unit there. 1 inch is, and then that would cancel because it's on the top, that's on the bottom. Your calculator is going to spit out 86.36 centimeters, but you would round that to about 86 centimeters because this only has 2 sig figs, so you'd round that to 2 sig figs. Now you can do as many of these in a row as you want. So let's try, you don't have to just do it stepwise. Let's say I asked you how many seconds are in a day. You can do this by hand or with a calculator. So there's more than one way to solve these a lot of times, but why don't you just try it this way? You say, okay, my given unit, I write first. That's my given, that's where I start the problem. A lot of students have a hard time on knowing where to start. Well, you just look at the question. You just say, okay, they're asking me for seconds. That's going to be the result over here. And I have to start with the given information. In a day is 1 day. How do I go from here to here? Well, you go through this. You don't have to do it in one step. If you look in this chart, well, there's no relationships or equivalent statements, conversion factors relating time between days and seconds. There is one you could write, but why don't you just take it stepwise? So you know that in a day there's 24 hours. So why don't you just take a day and cut it down into the next piece of time that's smaller, which would be an hour. We know that there's 24 hours in a day. So the new unit, hours, would have to go on top. Hour is usually abbreviated HR. And then the unit of day has to be on the bottom, like that. And then, so then if you want to cancel as we go, let me put that in red to highlight it. The day unit is on the top, it cancels with the day unit on the bottom. Notice I don't have, this is not a fraction or a ratio. I could put it over 1, but I don't need to. So if you start off your problem showing the work like this, it's fine. You don't need to put it over the number 1. And then the next fraction of time less than an hour would be a minute. There's 60 minutes in an hour. That's an exact number. These are definitions. So these do not influence the final number of sig figs in my answer. There's 60 minutes in an hour. The old unit has to be canceled, so it has to be on the bottom. I'm writing 60 minutes on the top, so the unit of hour on the top cancels with the unit of hour on the bottom. You'll see there's a pattern. The unit you're canceling is always on the bottom of the next conversion factor. And then you would write, we're almost there, we want to convert minutes to seconds. So the new unit has to be on the top, the old unit has to be on the bottom, and I know that in 1 minute there are 60 seconds, so minutes on top cancels with minutes on the bottom, and you would get 86,400 seconds as your answer. Now, again, I mentioned that this technically has 1 sig fig, but this isn't really a measurement problem. We're just asking for how many seconds are in a day. So it's just a simple question with no uncertainty in it. And these are all definitions, so we know those to be exact numbers. So your answer should not be rounded off in this particular case. Sometimes it's hard to understand that, but if you haven't measured anything, you don't need to do any rounding off. This is just a statement of fact. There's 86,400 seconds. There's no uncertainty in this answer. So there's no need to round. No uncertainty, no need to round off. Okay?